Hello students, let us prove today two theorems from the topic circle. Theorems are theorem of internal division of chords and theorem of external division of chords. To start with the first theorem, theorem of internal division of chords. Let us have its statement. Suppose two chords of a circle intersect each other in the interior of a circle, then the product of the lengths of two segments of one chord is equal to the product of lengths of two segments of the other chord. Now let us try to illustrate this by using a diagram. Suppose there is one circle with center P, and as we can see, chord AB and chord CD are intersecting at point E, which is inside the circle. So if it is the case, then we have to prove that the product of lengths of two segments of one chord, that means for chord AB, two segments are AE and BE, which are made due to the point of intersection E. So if we take a product of AE and BE is equal to the product of length of two segments of the other chord. So two segments of the other chord are CE and ED. So if we take a product of CE and ED, must be equal to AE into EB. That we have to prove. So for this diagram given is chord AB and chord CD of a circle with center P intersect at point E. That's given. And from that we have to prove that AE into EB is equal to CE into ED. So again, as we can see in the diagram, AE into B, that must be equal to CE into ED. To prove this, we have to do one construction. We have to join points A and C and points B and D. So that is the construction cross segment AC and segment DB. By doing this construction, we have got two triangles, triangle CAE and triangle BDE. We have to show that these two triangles are similar. If we can show these two triangles are similar, then we'll get the result. Now for these two triangles, we have the first pair of congruent components, that is angle AEC is congruent to angle DEB. As these two angles are vertically opposite angles, they must be congruent. Now we have another component, that is angle CAE is congruent to angle BDE, as both of these two angles are inscribed in the same arc, that is angle CAE and angle BDE are inscribed in arc CAB, and we know that if there are two angles which are inscribed in the same arc, those must be congruent. That's why these two angles are congruent, as these are angles inscribed in the same arc. Now we have two pairs of angles of these two triangles which are congruent. That's why these two triangles must be similar by AA test. That is angle CAE is similar to triangle BDE by AA test. As these two triangles are similar, their corresponding sides must be in proportion. Now we have to select sides that we have to prove. That means we have to take side AE. So if we consider the second and third vertex of the first triangle, then we get side AE. Its corresponding side is DE. So we have AE divided by DE, that is equal to, we need here again CE. So we'll take the first and the third vertex CE. Its corresponding side is BE. So that is equal to CE divided by B, as these are corresponding sides of similar triangles. Now if we cross multiply, we get AE into EB, that is equal to CE into ED. That is, we wanted to prove AE into EB is equal to CE into ED. This theorem is called as theorem of internal division of chords. Let us have the next theorem, theorem of external division of chords. Now this theorem is similar to previous one, only difference here is this time chords are intersecting at a point which is in the exterior of a circle. Let us consider the diagram given. Now for this diagram, if seconds containing chord AB and chord CD of a circle intersect outside the circle at point E, then in this case we have to prove that AE into EB, that is equal to CE into ED. So we are going to prove this one. Now for that one, let us have one construction. We have to draw segment AD and segment BC. So by doing this construction, we have got two triangles. We have to consider triangle ADE and triangle CBE. For these two triangles, angle AED is congruent to one angle which is a common angle. So it must be angle AED is congruent to angle CEB, as this angle is there in both of these two triangles. That's why these two angles are congruent, because this is a common angle. Then angle DAE is congruent to angle BCE. So it's given, we have to write the reason. So the reason is, these are the two angles which are inscribed in the same arc. So as we can observe, both of these two angles, angle DAE and angle BCE, are inscribed in arc ABC. That's why these two angles are congruent. Now, therefore, these two triangles, triangle ADE and triangle CBE, must be similar by AA test. So, triangle ADE is similar to triangle CBE by AA test. As these two triangles are similar, the corresponding sides must be in proportion. So, if we take AE, its corresponding side must be CE. So, we should write AE divided by CE is equal to, if we take side ED, that is third and the second vertex of first triangle, then its corresponding side is EB, and the reason is corresponding sides of similar triangles. If we cross multiply, we get AE into EB, that is equal to CE into ED. So that is, we wanted to prove AE into EB, that is equal to CE into ED. So this is the theorem which is called as theorem of external division of chords. That means if there are two chords given for a circle, if we draw seconds containing those chords, the seconds intersect each other at a point which is outside the circle. So if this is the case, then we have this product AE into B, that is equal to CE into D. So let us revise this one. Suppose this is a circle where chord AB and chord CD intersect each other at point E, which is inside the circle. Then in this case, we have AE into EB, that is equal to CE into ED, and this property is known as theorem of chords intersecting inside the circle. Now if we consider another diagram, so this is the circle where chords AB and chord CD intersect each other at point E, but now this time point E is in the exterior of a circle. Now if this is the case, then also the product AE and EB, that is equal to CE and ED. This property is known as theorem of chords intersecting outside the circle.